slopes. So as you can see, it goes back to trigonometry, but really we're not going to emphasize any of it right now. In a way, it is simpler than trigonometry because, like I said, it's just two numbers that are involved. Half of the time, both of them will be integers, so you'll have a slope of 1, slope of 2, slope of 1/2, slope of 1/3. What does it mean? It means very simply, slope of 1 is 1 and 1, 1 and 1. Slope 2 means 1 and 2, 1 and 2. Okay? Slope 1/2, it means that I have here, say, well, the one way is to do it this way. So you go 1 by 1 horizontally and 1 1/2 up. Okay, so that's a very simple idea of describing the angle of the straight line without trigonometry. So it is definitely about the angle. It is about steepness. Also, in comparison to trigonometry, you also can see how things go down, not just up. But also, it is simpler because you don't have to worry. You don't really have to worry, even though it's certainly convenient, to take into account think in terms of degrees as well as radians, and which one is there is not important. Either way, well, you probably need both. So this is what an example would look like. Angles, the basic angles are 45 degrees and 0 degrees and negative 45 degrees. Okay, but if you can certainly think in terms of radians, and we're gonna look into that later. This time, it is really the point that I'm making is that what's on the right is actually much more important, and it is, I'd say, easier to understand than trigonometry. So once again, slope of 2 is 1 up and 2 units, 1 right and 2 units up. So if the slope is m, any number, that doesn't really matter. It means that every time it's the same story. 1, you can always imagine yourself following a slope of m, 1 unit to the right and m units up. Of course, if it is a negative number, units up means that many units go down. Okay. So here m is positive, and then so the exact same idea. It's just the starting point is the same. It's still 1 unit to the right, so that part doesn't change. But if m happens to be negative, you're going to end up with. So I still say this. I say the same words. M units up, but m is negative. Okay, so m is positive, and then you go up, and then when m is negative, even though you say you're going up, but you're really going down. Okay, so that's the ideas here. So it's and then that you speak of 1 point at a time. So these 2 points then will lie on once constructed. These points lie on a straight line with slope m. Okay, but as we know, no matter which 2 points you pick in that manner on a line, they will produce the same slope. So it means that this construction can be used to construct many points on the line. So say slope 2. I can do this many times. 1, 1, 1. So right, 2 up, right, 2 up, right, 2 up. So it will be every time you'll have a staircase, just different staircase depending on the slope. So it is a slope is a proportion. It is rise over the run. It is the how fast you're climbing, assuming that your horizontal progress is the same. So you can just as well assume that you are moving horizontally at say 1 foot at a time, and then m, the slope, will tell you how fast you're moving up. Okay, so that's the idea of the slope. It is a really important concept. It is just about everything calculus relies on it, and you can see that the challenge of calculus is when you are not looking at straight lines. Okay, so you're looking at all kinds of curves. typically. Okay, and so that's our next question. But it's really not that bad, because at the very least, if you see a curve, what you can do, you zoom in, and then there's a chance that your curve is made of straight lines. Okay, and then everything applies to every little piece over there can be looked at. In that manner, you will know slope, and you'll know how fast you're growing in that particular location, and then you can see how that slope changes from point to point. Then that is, you will speak of acceleration then. Okay, so we'll get to that later, but at this time the slope is extremely important as it stands. The only one topic that remains here is the third way to represent a function, linear polynomial. So 3 ways to represent a straight line. So y equal mx plus b. The most recent one, slope intercept. Okay, then from earlier, we had this, ax plus by is equal to c. That's implicit or general linear, general equation of the line. Which happens to be a relation. So while this is a function, and as you can see, y is given explicit in terms of x, that's what makes a formula a function. This one is not. X is not. Y is not represented in terms of x, no vice versa. So that makes it a relation. So a relation between x and y is given by this this formula. But the straight line the result is still a straight line. The advantage is that this one includes vertical lines too. So function, that cannot be a function. But it is a relation. Okay. And then, so that's in chronological order. This is the way we did it, 1 and 2. And then there is one more, and that is the point slope form. Which is a function again. Okay, so the point, well, actually it's not a function necessarily. It could be a function, it could be still a relation. It is would be relying on y-intercept to understand that you still need slope, but y-intercept is really not that important. It is very narrowly chosen point on the line. So alternative idea is to choose any point on the line and use it as like an anchor. So remember, slope will give you the direction how to progress from that point. But then which point you pick? Any point should do. This one is, so once again, how that the first one is start at y-intercept, which is the point being 0b, and then follow the slope. That's the idea of the slope-intercept formula. Here we have start at any point meaning any point that we choose, x naught, y naught, and then once again follow the slope. So that's the idea. In case you haven't seen this before, the formula is this: y minus y naught is equal to m x minus x naught. Okay, so the point is explicitly visible right here. So these are the two coordinates of the point. Any point will do on the straight line, but suppose we have chosen one, x naught, y naught. And so it is a fixed point in contrast to x and y, which are variable. Okay, so we still have those axes somewhere, x and y still vary. You can think of y depending on x, even though this is a relation. Once again, y has not been expressed explicitly in terms of x, but you could, if you just take y naught and pull it to the right-hand side, then it will be explicit and it will be function. But this is just, why the advantage, why we choose it to put it this way. It's just easy to remember. And as you can see, why not is on the left. So the symmetry of the formula helps you to remember and understand where it comes from. So you have y minus y naught on the left and x minus x naught on the right. Okay, so once you see that, you realize that, well, the meaning of this versus the meaning of that. What are the meaning of these two expressions? What is this? Let me try to plot this for you. X naught, x. Y naught, y. Okay, so y minus y naught is this. Yeah, there is another word for it. It is a change of y, that's right. So I was driving at the other word that we started with. Remember what it's called? It is the change of y. And the other one is the change of x. X minus x naught here, change of x. I was hoping you'd remember the rise and run words. These are the rise and run. Look at the picture. So this is the run, and this is the rise. Okay, you can clearly see them on the graph of the function here. So the formula is made clearly of two things: the slope, so m. Also on the right is the run, and on the left you have the rise. So certainly, I mean, if you take that formula and just flip it, not flip it, but rather what? M is equal to y minus y naught over x minus x naught. Okay, so rise over the run. Right. So that's the point of putting a formula in the particular order these quantities so that they would become recognizable. So you have the y minus y naught is how far you deviate from that point. So you move from point x naught y naught, right, over here. You're moving to another point which happens to be, so this is x naught y naught, and you're moving to another point which is xy. That arbitrary point on the graph that is sliding back and forth with x and y, and then you look at the rise over the run. So we have the same story. So this is, we don't use this equation for a single reason. I mean, this is just exactly the definition of the slope rise over the run. We don't use it because it is possible that we would have 0 at the denominator. So hypothetically, if that equation would not be an equation of a straight line, because you will never have x equal to x naught, so there will be a domain will not be everything, and we want to have if it is a linear polynomial, which it is, the domain is everything, the implied domain is everything, and so we don't want to have any division if we don't have to have it. So then, as you can see, the slope has this thing of it's defined as a ratio of two things, so it's possible that you end up dividing, and so that's a problem. A relation between these three is clear. You can just start moving things around. For example, how do I get from number 3 to number 2? Well, I choose my point. I choose my point x and y to be what? The point slope form is, point slope form, the last one, has advantage over the number 2 slope intercept form, is that the point, this is the match. Point, it is still mentioned, point on one hand and slope on the other hand. So the slope is present in the name, as well as the other part is about a point. Okay, it just happens to be a generic word point in the latter case, and in the former case it is intercept. So we choose our point to be intercept for the second formula, while the third one has any point will be fully applicable. So you just choose that point in the third formula to be the y-intercept, and you have the original formula. So I choose x naught to be what? What should x naught be? Well, the x naught, y naught is the y-intercept. So what are the coordinates of the y-intercept? Which one?
X minus x naught.
No, I need x naught and y naught. What should be the choices? Those are the coordinates of the y-intercept. So B is what? B is y naught, right? And x naught is, remember what x-intercept, y-intercept is? B is the y-coordinate, and x-coordinate is 0. Okay, so the formulas are interconnected. They're technically they look different, but it's the same equation. It's the same line. The same equation ultimately, if you go through the algebra and move stuff around, you just can transfer one into the other. So it's the same thing. And this one is the easiest one. How to get from one to the other. You just choose the point in the point slope form. Choose that point to be y-intercept, and you have the original formula. It looks slightly more complicated, but not really by much, right? So we have an extra term to worry about, and that is x naught. Okay, so either you have m and b, 2 parameter, we have 3, m, x naught, y naught. So that's what the last formula is. Okay. Any questions about this? Okay, so the topic has been of how to create functions through algebra. So the two algebraic operations we have been using are only addition. So this one addition, subtraction, same thing, and multiplication by constant number. Okay, so I wanted to move to the next step and the next level, and that is this. It is still multiplication, but the difference is it is multiplication by the input itself rather than by constant number. So you can compare is 3 times x or x times x. So same naturally, it's the same. In either case is multiplication. But this one is constant. So x is taken 3 times. And that's what it represents. X times x is not constant. So the input multiplied by itself. Then it matters what we're talking about. If you think about any kind of practical functions, then the former would be, say, some quantity is taken 3 times. That's it. So maybe the temperature rises by 3 times or something like that. Or the temperature depends on time, x is time, and the temperature grows at a factor of 3. So in other words, quantity repeated some fixed number of times. The second one is slightly different. It is very frequently is supposed to indicate things such as, for example, the area. Okay, so if the input is x and you take x squared, what you do is you construct a square, and then x squared is the area of the square. Okay, so x squared is the area of the square. What square? X by x squared. X by x squared. So 2 sides of the square is x by x, and the area is x squared. Okay, so that's the geometric meaning of x squared. Okay, so why we care? You can imagine that if we move on to x cubed, what's the meaning of x cubed?
X times x times x.
Yeah, geometrically.
The volume.
The volume, yes, of what? Of what? Of the cube, yes. Of the cube, x by x by x. So looking like this. it's not as clear as you go to the next power, to fourth power, what it's supposed to represent. But if you can imagine fourth-dimensional cube, then there you go. That's it. Okay. So that's the geometry. That is why we here. But really, it is at this point is just a computation, and so we're going to see it, see how it is computed. So it's computed slightly different from 3x. So you have to sort of, if x is the input, then you have two copies of x, and then you multiply them. Okay, so x the input, you take that number to make two copies of x before you can multiply them, and before you can do anything with them, and then you the output is y. Okay, so that's how the function works roughly. So very different from 3x. You can still describe it as once you get used to it, you just say, as I have before, square it, and that's your function. Okay, just if you understand how to square a function, a number, then you're fine. But our interest is right now is not how to compute it, because it's really straightforward, but rather what it's graph. It's graph. Well, everything we want to know about the function, we want to find out. So which is what usually it is domain, values, graph, and so on. Okay. The codomain sometimes is also interesting, so we'll look into that too. But firstly, domain. What is the domain? What is the implied domain of f of x equal to x squared? Well, remember, domain is supposed to exclude all the values of x for which the function doesn't make sense. So can you think of any values of x for which x squared wouldn't make sense? Find the answer. Domain. Domain? Implied domain. So any x such that x times x doesn't make sense. Or impossible. Or computer breaks down, anything of that nature. That's what domain is. Or real numbers, right? So multiplication is, so that's the answer. The answer is indeed negative infinity, infinity. Multiplication does not present any problem ever. You multiply two numbers, the product always makes sense. It is division that might cause, does not have to, but might cause problems, as well as roots also might cause problems. But these, so far, we did not touch on division, so we'll just stick with the multiplication. So domain is everything. Okay, so the values are, we just create a list of values in order to get a sense of what's going on. So you pick a few values, then they spread out through the domain. And the domain is everything, so just as well pick a few like this. Compute the values. 9, 4, 1, 0, 1, 4, 9. Okay. the pattern starts to appear. Well, certainly you probably, I don't have to explain to you how to multiply negative numbers. So negative number multiplied by itself will become positive. Okay, so which means that the symmetry is this. So even though the inputs are different, the outputs are the same. Okay, that will be visible once we start plotting. It will be even more visible, but it is somewhat visible already. So the repetitions are there. So which means that if you want to think about visualizing a function with arrows, there will be arrows arriving to the same destination like this. So if you square 1 or -1, the result is the same as 1. Okay, so we don't assume that the outputs are also, once inputs are different does not mean that the outputs are too, which has been the case, by the way. It is, well, with one exception, linear functions, linear polynomials, have this property that the different inputs produce different outputs. Okay, but not so once you move to quadratic functions. That's not the case anymore. Demonstrated by this little computation. But you won't see it as easily if you will see it easier if you plot a few values or these values on the graph on the xy plane. And that's the point of plotting graphs, is that you might see a pattern or absence of pattern once you have a few points available. So I'll start with the 0, which happens to have only single value. The only output 0 is from 0. Okay, so then I have 2 points, -1 and 1 over here. So this is like this, -1, 1. And this is 1. So I progress to the left and to the right by 1, and then I make one more step to 2, like here, -2 and 2, and once again they produce the same result. Oops, like this, two values here and there at 2. And then I need more room here. I make one more point to the -3 and 3 here. So I'm utilizing the symmetry that we have noticed in the graph, in the table of values. So say maybe here. And this is 9. Okay, and then I have 2 more points. Okay, so that gives you an idea of nobody would correct me. I was I was supposed to plot 4 here, right? Okay. So this is 4. So each point. Each row in the table produces a point on the xy plane. Okay, because 2 numbers in each row of the table and 2 coordinates for each point on the graph. Okay, so usually you just stop here, or you usually don't stop here. You try to understand what it might be a curve. So missing values here. If we are to consider the whole domain, because we picked just the integers from the domain, and there is infinitely many if we go to -3, infinitely many values remaining, infinitely many if we go beyond 3. Also, and then there are more infinitely many values between each of them. Once again, infinitely many values that we have missed between 0 and 1, infinitely many over here, and then here too. So there are just so many numbers that we have no chance of getting them all. But fortunately, the picture tells us roughly what it might look like. And so then we are filling in the gaps, literally. So we cannot do that with numbers, well, unless we do more computations. But the graph allows us to have infinitely many extra values with the stroke of a pen. So we're like this, maybe. So I'm trying to make a rough picture so that you can see that what computer does isn't really not such a big deal. We can do it with just by hand. So you try to make it into one curve that does not make that looks smooth, does not have breaks, satisfies the vertical line test, remember, and does not make sudden turns. So, for example, I didn't do this at the bottom. I didn't do it like this because that is a sudden turn, and even though it is possible, we do know that it's not the case about this curve. Okay, so once again, no sudden turns, no breaks. So this is all I'm trying to avoid, and almost like 99% of the time, it is indeed your choice to avoid these will be the correct choice. Okay, so once again, abrupt jumps or change of directions. So why this is important? Probably worth mentioning. Think about motion. If our function represents motion, and this is a function that does represent motion. As a matter of fact, if you're dropping an object from a high place, that's how it will be roughly developing. It will be going slow and faster and faster and faster. So if we are representing motion with our function, then avoiding those events that I plotted on the right, it makes sense because the first one is what is it? It is a jump from one location to the next, also known as teleportation or something like that. So you certainly, if you're studying some kind of a motion of that is real, you want it to continue to go in a continuous manner. So you between two points, if you're here and then you're here, then you all visit all the points in between. Okay, so you don't want to jump. Okay, so that would be just not realistic if you're doing any kind of modeling of motion. And that's for the first one. And for the second one, what is so sudden? Think about the second picture, why it is bad from the point of view of motion. Not as bad as the first one, but still bad. What's so bad about the second one?
The motion of an object has to slow down gradually when we go in the opposite direction.
Right, exactly. So that's what it shows. It's sudden change of direction, sudden change of not sudden, instant change of direction, and once again, you probably don't see that happening even when you bounce a ball off the ground. It still takes time to contract and turn around. Okay, so these extreme cases that you can easily imagine mathematically in real time, they don't happen, and that's why we try to avoid them. And all the functions that we're looking at are pretty much all well behaved, so they're not like this. So you have to make it up in order to make them poorly behaved. One exception is the absolute value function is kind of important, and it has the V shape like this. Okay, but generally we are able to avoid these problems. So the general picture now you can certainly see it and do it with any graphic calculator. The graph of my function will be a parabola, known as a parabola, which at this point is not as how should I put it? Not a discovery as much as an explanation. So we don't discover that the graph of x squared is a parabola, but rather we say, well, this is the graph of y equal x squared, and we call it a parabola. So it is easier to explain parabolas with quadratic functions than try to do it vice versa, and try to explain quadratic functions with parabolas, but it works both ways. You can look at the graph of this function many times, and of the parabola, and realize some of the behaviors that are to be recognized later on. And later on, you see a graph, and you say, well, that looks like a parabola, which is maybe useless. But if you say, well, a parabola, the graph of a parabola is the graph of what? Of a quadratic function. So maybe what I'm looking at is, in fact, a quadratic function. So that would be quite an insight. So then what is so special about this curve? Well, it goes down and then goes up to begin with. Okay, so like this. Once again, it does not have any of those nasty behaviors, breaks or sudden turns. Okay, then what else do you see? Up, down, no bad behavior. What else do you see? Any patterns? Well, that like I said, up and down. What else? So and it purely goes down and purely goes up, so it does not stop. If we zoom in, it will continue that behavior. There is nothing like you cannot imagine that we zoom in and then we look and then it behaves like this. Also no. So it goes down permanently on the whole interval, and then it goes up. How about you compare the left side to the right, left half to the right half? They're symmetrical. That's another big deal. So it's symmetrical about its about the vertical line. Okay, so symmetrical. What does it mean? It will be discussed at length. So important it is. So vertical line, which is specifically the y-axis. So you could symmetrical. Symmetrical is a generic word, but this one is a specific symmetry. And how would you describe it? The symmetry. So the symmetry means that it looks like what's on the left and on the right is the same, but not exactly. So how would you describe the symmetry? Oh, if it's not, it's not symmetry. But the point is, how do you transform one into the other? It is a mirror image, right? Right. So it's a mirror symmetry. A mirror symmetry, and that literally means if you imagine, we'll try to imagine that this is drawn on a piece of paper. Okay. Well, in fact, let me try to do this. So this is a piece of paper. Okay, so these are my axes. Okay, this is my parabola, like this. Okay, and then I take a mirror. I take a mirror and put it like this. So this is on the flat surface, is my xy plane, and then this is where I put my mirror, like this. So this is the mirror. It will put it on to follow its edge, to follow the y-axis. Okay, then you see what I'm saying? If I look at the mirror, what do I see? Yeah. But the point is, it looks the same. So I have mirror up or down, and I'm looking at it, and it looks exactly the same. Because the mirror image of the right branch, I cannot see through the mirror, but if I look at it, I see the right branch reflected in the mirror, and it's as if I'm seeing through the mirror, and I'm seeing the left branch. So over here, there's a mirror or glass. That would be a question to ask. So there is something there standing, which looks like a mirror or maybe glass, and I'm seeing through it. Am I seeing through the glass, or am I seeing the reflection in the mirror? It doesn't matter. It looks exactly the same. Okay, so that's the mirror symmetry. Okay, so there will be more and more functions like that, and well, you can think of probably mirror images, objects of mirror images. They're just everywhere. A circle has a mirror image, so if I do the same trick and I put a circle here, it will have the same property that its reflection will look of the reflection of its right half will be the same as its left half. Okay, faces have mirror images, more or less, roughly. pair of glasses has a mirror image, a mirror symmetry. Okay, and so on. So that, but we'll look at the functions, because if we see that symmetry on the picture, then we make a conclusion about its numerical behavior. And if we can trace back that mirror symmetry to numbers, so let's do that. So mirror symmetry. So where is it? In the table. Here's the table. Now on the left, do you see where that symmetry is? Well, maybe before that, there is another way to think of mirror image, and that is instead of having mirror, you just take take the piece of paper and fold it like this. And once again, the right branch will land on top of the left branch. Okay. So, and then you can see that in the table. That's the fold. That's the fold. Is this? This is the fold. This is the symmetry. Whatever to the left or numbers less than 0, that's 1/2, and the other half is on the right, and it produces the same exact values. And that's the and this is the fold, if you like. This is the fold. So not only the graph will have symmetry, but also a table, if you do it the right way, table has symmetry too. Okay, and the symmetry right there in the middle, about 0. Everything is repeated. Okay, so so that's a quadratic function. Something I want to emphasize about quadratic functions. So the parabola is all the descriptions that I have here. They're described parabolas, but you can sometimes tell parabola from others, which we'll also discuss shortly. But you can tell if you look carefully at the bottom of this graph, you can tell that it is not a parabola. You see the difference? It is flat at the bottom. Okay, well, I lost symmetry, unfortunately. So the description that we have had fully applies to this function over here, but it's not a parabola technically. The parabola is the graph of the quadratic function. This one is not, and can you see the difference, right? The thinner tip or flatter tip. You can actually tell it by looking at it. And this happens to be, by the way, x to the 4th. X to the 4th, it has the same behavior, so it has symmetry. It goes down then up, but it just does not do it in a slightly different way. First it is going down very fast, then slows down significantly, and that's why you have that flat bottom, and then it has very fast growth afterwards. So that's the something to watch out for. Now, okay, so where do we go from the square? Y equal x squared. Next. What's next? Next level of complexity. What? No, yes, but that's one way to proceed. Actually, I'm talking about the quadratic functions, so quadratic polynomials. So, I don't know, 2x squared minus 7x plus 8. Like this. A quadratic polynomial. So, so the computation is certainly more complex, but still no division. No division. So nothing to exclude. Nothing to exclude from the domain. So the domain is, once again, everything. Negative infinity plus infinity. Okay. So to begin with, and then their shape of the graph will be. I'm not gonna go into the details until we move on. But it's still a parabola, except it is located elsewhere. located elsewhere, which means that the y-axis is not the symmetry, the axis of symmetry as we call it, but there's still an axis of symmetry somewhere. Okay, so that's what we need to learn in addition to what you already know about quadratic polynomials, and that is the what is that you already know or supposed to know about quadratic polynomials or quadratic functions or quadratic equations. What quadratic equation what first comes to mind? Yes, f of x. This is the general form. This is the general form of a quadratic polynomial. So with three specified or unspecified coefficients. But then you make a next step. Remember the quadratic formula? The quadratic formula? Well, you don't have to. I mean, you do have to remember it at some point, but you should at least remember what it's about and what it's for. What is it for? Quadratic formula? What? Yeah. Okay. Well, what is it for? Okay. I guess we'll just resume tomorrow. Next time.